All right, so we're going to cover some background material. If you had me for a class already, which I see some of you have, it's a repeat from other classes because it's general information at the beginning. But then we quickly move into thermodynamics related materials. So we'll cover chapter 1. When you are on an exam, I need you to be clear about what is your answer. So use a box on your final answer. Put an equation inside the box, meaning there's an equal sign, something to the right of it, something to the left of it. Something to the left of it's what you were looking to solve for symbolically, like T for temperature, P for pressure, W dot, whatever. And then to the right side of the equal sign, a numeric value with units. Here are some examples. Look good? It looks good. Does this look good? Looks good. Does this look good? Look good. Notice also everything's to how many significant digits for this number? 3. How many significant digits for that number? 3. How many significant digits for that number? 3. All right. What about a mistake? What is the mistake here? No units. What's the mistake here? No equation. What's the mistake here? Yeah, this is a significant. How many significant digits are there? 6. Tell me your age in days good to 6 significant digits. Tell me your age in minutes good to 6 significant digits. Might be a good homework problem. All right. Order. What's this mean? Should be right and left. Get the right over and the left over. What you're looking for equal to what you're asked, the answer, what you solve for. What's wrong with this one? Somebody says the professor wants the box. And then a little note, find it inside. Right? Find it inside. Yeah, everything's in the box, professor. No, box for the final answer. This is a run-on equation, intermediate steps not included. And this is not a box. Underline is not a box. You saw that one joke probably. The student was given this for a trigonometric exam. 3, well maybe this looks like here. 4, 3, 5, oops, sorry, that's the answer, x. And then they say find x. Find x. Come on, I can't write. And know what the student did? Here it is. And it should be 25. X is, yeah, right, 5. Square root. Right? All right, 3, 4, 5 triangle. That joke went over like a lead balloon. All right, let's continue on. Fluid. What is a fluid? A fluid is different from a solid because a fluid continuously deforms when subjected to a shear force. So if I take a block of a solid and I attach it here, then I attach something and pull on it, it'll possibly deform a little bit, but then it'll stop deforming. Even though I have a finite, non-zero shear stress, I'm trying to shear it, pull it at the top. But if it's a fluid, it'll shear at a continuous rate proportional to the force that I apply, proportional to F. So it'll continuously deform when subjected to a shear stress. Liquids, gases are good fluids. Solids are not. Duh. All right, continuum model. We know that real material is made up of voids, and we have little nuggets known as molecules flying around. Let's say helium or diatomic oxygen. Those little nuggets or molecules spend most of the time traveling through the void or through the vacuum until they collide and hit somebody else and bounce off a solid surface or another oxygen molecule. So most of the space is filled with voids or a vacuum, and very little is filled with the nuggets of chunks of material flying around. But what we do is we say it's smooth, it's a continuum, and that's our fluid. We neglect that void nature of the material. Unless we go down to rarefied flow conditions, then you do have to worry about it. Incompressible versus compressible, it's how the density changes. Is the density a constant? If I boost the pressure but the density doesn't change, incompressible. If the density changes, it's not equal to a constant, then it's compressible. Steady or unsteady, it's how does it change with respect to time? Does the temperature change with respect to time? The volume change with respect to time? The pressure change at any point or location or for the system change with time? If it doesn't, hey, then it's steady. If it does, then it's unsteady. True? All those terms should be very familiar to you. We have a group or classification of the flow which is external to an object. Typically we have solids and then we have fluids either through or around the solid. So an airplane wing, solid surface, and we have the flow around it. It's external around the wing. A ball, either a soccer ball, football, golf ball, and we have flow around the ball. Or a rocket, here the rocket is going up in maybe the air. That's a bad looking rocket, but there you go. And the air could be modeled as flowing around it, and the rocket stationary, change your reference orientation or reference condition. And then a car, automobile, same thing, going down the freeway, and the car will have some flow around it. In each of these, what you pick up for the car is you'd pick up a drag force. For the wing, you pick up a drag force as well as a lift force so that the wing gets the aircraft off the tarmac and up into the air. And a lot of times, depending on the curving of this ball, you can get the ball to do all sorts of motion with the baseball, right? Curve, sink, and some other motions. Other great classification of flow is not external, around the surface of the object, but internal. So a pipe, there's our solid surface, and we have the flow going through the pipe. A duct, that would typically be for flow of air. A lot of air goes through ducts, and they're not necessarily round. They could be oval, they could be rectangular. We also have valves, T's, elbows to connect straight runs and change them, divert them, and join them. So all that's internal, so the flow is confined by a solid surface. No slip. What happens at this solid fluid interface is really important. So the fluid that's intimately close to the solid is at the same speed as the solid surface. If the solid surface is at rest, the fluid's at rest. Now, very small distance away from the solid surface into the fluid, it can be moving. But we call this no slip boundary condition. So there's my solid. There's my fluid flowing over it. And the fluid right adjacent is no slip. It's at the same speed or velocity, if you want to call it velocity, thinking of a vector quantity, as the solid. So now we have a region which is around or close to that solid, between the solid and the free stream region of the fluid, where there's a layer and it's impacted by the presence of that solid boundary or that solid surface. So if I have a plate and the fluid is approaching it like this, far away, if this is a uniform flow field, the velocity out here will still be uniform. Everywhere it'll have the same velocity. It'll be to the x at a certain magnitude. But as you get close to the surface, it's got to go to zero, and there's a sharp transition. And I've even exaggerated that. It's very small. And it's in this region right in here, it's the boundary layer. It's a layer of fluid that's felt the presence of that solid. Laminar flow. Well, laminar is like layers. Organized flow, it's the layers of the flow stay in the same relative position to each other. So they may just stay in those layers as they flow around. it's typically slower flow. That's how you get laminar flow. It just typically goes slower. Now, faster flow, what happens is it doesn't like to stay in the layers. It likes to cross lanes. I've seen some people driving on the freeway like this. They like to add turbulence to the cars, choo, 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 right? And anyway, that's very random in appearance, although the people who study turbulences say there's order to it. Well, yeah, you got to slow down the camera and really study it. You see things that are really shedding and moving coherently like a dance. But it to the eye and for the introductory purposes, you can just think of it as random, but it's not. But or disorganized. And so a fluid packet that may have started here ends up going way over here. And a fluid packet that started here, instead of just going on this type of path, it may end up way over here. Switching places and mixing. It's good for mixing, great for mixing. Turbulent flow. Also, it's associated with faster. When it moves faster, you have more propensity to be turbulent. Why? Well, it's characterized by a dimensionless parameter called the Reynolds number. Hey, is this the whole class, or is this just chapter 1, the introduction? The whole class. Why not put it all in the chapter 1? And then delete chapters 2, 3, 4. No, just joking. But Reynolds number, how many people have heard Reynolds number? Yeah, if you've taken the physics class, right? So it's a ratio of inertial forces or inertial pressures to viscous. Okay, inertial. Well, if I could take anything, let's say it's a chunk of fluid. What does it have inertia? How do you describe its inertia? Well, if it's at rest, it has no inertia, but if it's in motion, it has inertia, right? It's like it's linear momentum. It would be the mass times v, the speed. Higher the speed, the more inertia. And we'll talk more about viscous, but viscous, a packet by itself, really, you don't talk about viscous or viscous forces, you talk about adjacent packets of fluid. So if one fluid's trying to go fast and its neighbors are all going slow, the neighbors have a retarding effect, pulling back on the fast packet. And the fast packets pulling on the slow packets of neighboring fluids to move them forward through viscosity, viscous effects. All right. And then I like to give this poor analogy of kindergarten, because when I was in grade school, every now and then the teachers would get mean and they'd say, everybody, I don't want you to get out of line. We're going down to the cafeteria. We're going to exit, come out this classroom door, all march down all together, the long hallway, not get out of place, get our food, get in line, stay in line, sit at the tables, get back to the classroom, hold hands. The teachers made an instant increase in viscosity in the kindergartners. They all had to hold hands. You couldn't break loose and be the little individual kindergartner that wanted to run around and visit your friends, right? But then when the class was done, in the class that let out of school, it's all mayhem. Students are running this way and that way, crossing paths, bumping into each other. Got to see our friends over there. And that's kindergartners. Don't you remember? Yeah. So that's my quick analogy there. The Mach number is another dimensionless ratio, just like the Reynolds number. One time a student came up to me, Professor, I failed fluids, but I know it. Just give me the final exam. I said, oh, come on, I don't want to do that. If you failed fluids, you probably didn't learn fluids. I learned fluids. I learned it all. Let me just ask you a question. Reynolds number. What are the dimensions in SI units on the Reynolds number? You know, the kilograms, meters, kilogram meter per second squared, you know, newtons per meter. What are the dimensions in SI units for the Reynolds number? Well, it's a Reynolds number is density times a length, and then viscosity is in there. I can figure it out. It wasn't a very hard question. It was a very easy question. Anyway, it's a dimensionless number. No units. And he argued with me. No, it has units. You are ready to take fluids again. There was a reason, unfortunately, that the professor before me assigned that grade. Same with the Mach number. Are there dimensions to the Mach number? There's magnitude to the Mach number, but it's a dimensionless number. It's a ratio. It's a ratio of the speed of the object through the fluid or the speed of the fluid, whatever it is. Typically it's object through the fluid, some speed through the fluid compared to the speed of sound in the fluid. And that speed of sound can change if your fluid's a liquid or if the fluid's a gas, hot gas, cold gas, things like that. And then we typically spend a lot of time in this class on subsonic flow. That's the Mach number is anything less than 1. When the Mach number is definitely less than about 0.3, compressible effects even for a gas are negligible. Most of the time. A good cutoff. Mach number, unless you're really going fast in the flow, airflow, your compressible effects are negligible. And then you talk about sonic. What's that mean? Mach number is equal to 1. It's going at the speed of sound. Now, I know you could buy airplane tickets and fly in an airplane and go to France or somewhere. What was that, a Concorde? That went over like Mach 1. It was supersonic aircraft. True? I don't think they fly it anymore. I think it's done, right? But that would have been pretty good. I don't know what the airplane tickets cost, but it was probably a pretty penny. So anyway, a lot of military aircraft definitely go above Mach 1. They go supersonic. So that's Mach 1 greater than 1, supersonic. And at hypersonic, there are applications where the Mach number is in the range of 10 and above. They're typically, I don't know the exact cutoff, but it's probably about 10. You have ballistics, shoot some projectile, want to get over there fast to do some damage. It's coming out the barrel pretty fast. Hypersonic. The system, it's whatever you want to study. The surroundings, everything that's not in the system. How do you separate them? Introduce a boundary. Dashed line. Make sure it encloses. That's not a good boundary. Make it enclose something. Right side, left side, something. All right? So there's our quick definition of system, boundary, surroundings. It's just like a free body diagram. You have to be clear in statics of what you're analyzing and apply the principles of statics, sum of forces, sum of the moments equal to 0, to a clear free body diagram. Same here in fluids and in turbo, systems, surroundings, boundary. We have open systems, closed systems. And so if you wanted to analyze flow through a pump or turbine or a nozzle, use a control volume. It's an open system analysis. If you wanted to analyze gas that's trapped in a piston cylinder that's compressed, heated, expanded, cooled, use a control mass or a closed system. This is always hard. You've heard of dimensions, primary dimensions, or fundamental dimensions since maybe not kindergarten, but way back, come on, in high school for sure. And I'm sure that's been repeated in a number of classes, or at least it's in the beginning of the chapter of the textbook that you bought for a number of classes. True? Might want to look there. How many primary dimensions are there in all of science and engineering? The primary building blocks upon which you can get derived or secondary dimensions and express things. Kind of like, what are the fundamental building blocks? How many are there? 7. And what are they? That's the 7. Okay? So mass is a fundamental, primary dimension. Length is one, time, etc. Now, once we've said the dimension, then we could talk about units to quantify that measurement of that dimension. So you can say length is a dimension, but you either measure it in feet, miles, inches, centimeters, millimeters, kilometers, you just measure it in something. So in the system, the international system, previously known as metric, sometimes still called metric, MKS, it's a meter. meter for the length, a kilogram for the mass, and a second for the time. CGS, it's a gram, it's a centimeter, and a second. I should have put them in the other order, shouldn't I? Put them like that. Length, mass, time. That would have been lined up with MKS. In the United States system of customary use, customary systems of use units, what we have is foot, pound, second. So foot, force. Well, okay, call it a pound mass then. Pound mass, second. An inch, pound, mass, second. All right. Temperature, Kelvin. Amount, mole or kilomole. What's the difference between a mole and a kilomole? That's not a trick question. It's a kilo, 1,000, that's all. Which one's larger, the mole or the kilomole? The kilomole is larger. It has more number of particles in it, right? All right. True. It's like, look at a dollar or $1,000. You know, which one's a larger magnitude of money? $1 or $1,000? I think I take the $1,000, right? All right. Current, ampere. Luminous intensity, candela. That's a CD. All right, candela. We just don't use this light intensity, and the current is very straightforward. Now, what about derived or secondary dimensions? Something like speed. Speed is a length per unit time, true? So in the SI, meters per second, foot per second. How about area? Meters squared. What's a force? Uh-oh. A Newton, which is, you can break it down into one of the 7 fundamentals. Kilogram, meter per second squared. What's a work? Same as energy? Joule, excellent. Which is a Newton times a meter, which is a kilogram meter squared per second squared. So you can break it down to the fundamentals, that's all. Can you really express everything in science and engineering in terms of these 7 primary dimensions? Yeah, right. That's the point of calling them primary or fundamental, and then the secondary or derived. All right, there's a difference between mass and weight, and I know that those that have had me for a class before, and I typically try to explain this in almost every class I teach, because unfortunately too many students will even go through the whole program and they won't have a really good grasp on difference between mass and weight. And you're saying, you gotta be joking me. Okay, well, anyway, let's try. So if I have a mass of object of mass m, and it's in the gravitational field, which means it's in the presence of a big chunk of mass, typically something we're standing on called the Earth. And then mass attracts mass, and so you feel it and express it as a gravitational acceleration, g. G, true? Everybody's heard of g. What is g in SI? 9.81 meters per second squared. Oh, you're good. You're awake. And then g in US customary. 32.2 foot per second squared. Got it? Right. So if I want to know now the weight, I don't drop it and let it fall. I support it so it doesn't fall. I put it on a scale so it stays stationary, it's not accelerating, falling toward the earth, true? And when I put it on something like that, I have to support it with a force that's equal to its weight. Free body diagram, true? W down, supporting force up, right? So the weight is equal to m times g, true or false? The product of m times g. Do the units work? Did the weight in SI come out to newtons? Yes, they do. Let's check that. Let's say I had 1 kilogram for the mass. I have g 9.81 meters per second squared. I make the product to calculate the weight. The weight is equal to 9.81 kilogram meter per second squared. I multiply by 1 to convert the units. It's a unit conversion factor. True or false? What is the unit conversion factor that I want to use right now for this one? I want to use that a Newton is defined as 1 kilogram meter per second squared, which I can rearrange to be either 1 is equal to a Newton times a second squared over kilogram meter, or it's also kilogram meter divided by Newton second squared. Professor, you're confusing me. You mean this is equal to that? It's the reciprocal. It's either one or, it's upside down. Is this equal to that? Yes? You're absolutely right. You're absolutely right. It's equal to that. So which one do we want to use? Version A or version B at this point to replace for 1? Use version A. True. So we go in here with a Newton second squared divided by kilogram meter. All I did was multiply by 1. And away you go. You do the cancellation, kilogram, meter, second squared, second. You're left with Newton. So 1 kilogram mass has a weight of about 10 newtons. Does that make sense? So everybody that grew up in a country where they talked kilos and meters, and everybody say, when you go to the gym and you need to weigh yourself, right? And you step on the scale. And then somebody says, hey, how much do you weigh? You say something like 300 newtons. No, what do you say? Who knows their weight in kilos? You do?
Yeah.
About what?
63.
About 63 kilos. All right? You do?
68.
68. Wow, you guys are great. There was a lot of hands. I won't pick on any more students, but this is nice that you tell me. What's your weight in newtons?
68 times 9.3.
About 680. True. True. But nobody ever says, hey, what's your weight? 680. No. Seriously, right? So they're going to report their weight in kilos. They're confused, the SI people. Sorry, just joking. All right. But now what we want to do also is come over here, and we want to do it up for the weight and the mass in the United States. So in the United States, what we have is we like to talk about the mass being maybe 1 pound. Okay, put an M there so I'm clear. It's 1 pound of mass. I'm talking 1 pound mass. I forgot. Back here when I talked about slugs, did I ever mention a slug? 1 slug, right? You've read a textbook. You actually read the book, and it said, hey, in the English, they use slugs for mass. I've been in the United States since I was born. Some of you have been in the United States since you were born. How many people can converse with somebody in the United States about the mass in slugs? I want to see the hand. But some faculty actually like, oh, I'm going to teach slugs. Why do you teach something that's never used? It's like, it's not used. Well, we got to contrast. That's the British system. The British abandoned it so long ago. They don't want their name associated with it anymore. They're SI. The imperial system. No. We're talking in the United States, the man on the street, the customary unit, he wants to talk about his weight. He's not reporting his mass in slugs or his whatever. He's just not going to do it. There's nothing. No food label in the United States has, buy this, it's 20 slugs. 2 slugs, whatever it is. Now, just before we get rid of slugs, because really in the slugs is something you step on in the night when you're walking around and the thing is crawling across the sidewalk, and it's by accident because you didn't mean to kill it and smash it. But that's what a slug is in the United States. But if you really wanted to think about it as the textbook definition of mass, Is a slug kind of big or small? Is it something I just slip into my pocket and don't even feel as I walk around? Or is it if I, had to carry it for a mile, I'd be beat and sweaty? Or I couldn't even carry it for a mile. It'd be too big. How big is a slug? For those that read their textbooks and tried to learn something about slugs. It's around 32 pounds. That's not a trivial amount of mass. It's pretty big, actually, right? All right. Also, we always do this. Yeah, anybody has a water bottle, this gives you a good feeling. There's a water bottle right there. So how much is in that water bottle? Is it 500 milliliter?
Yes.
All right, so hold that up. Everybody look at the water bottle. Look at the water bottle. That right there is about 1 kilo. No, it's half a liter, so it's a half a kilo, right, of mass. So it weighs, and you're going to talk or feel weight in kilos too. And then it's about 1.1 pound. So that's roughly a pound. Okay, so it gives you a sense of a pound. Okay, slugs, 32 of them. Lot. All right, so now we're going to do the weight of 1 pound mass and the Earth's gravitational. So it's 1 lbm times 32.2 foot per second squared. What is the those that have taken me before, you must restrain yourself. I know you learned a lot. I know you've learned this, but those that have not had me for a class before, this is their opportunity to try to glean something. What is the weight of 1 pound mass in the Earth's gravitational field on the surface of the Earth, where g is 32.2 foot per second squared? And the question typically comes and says, well, it's going to be 1 over 32 lbf, or 1 lbf, or 32 lbf. Okay? So I think I've had some people who already take me before. You already took me before. You can't speak. You can't speak. You have to say, oops. Even if you never pass a class with me, you still can't speak. Only those who don't know me. How many people have never had a class with me? There's only a handful, maybe. 1, 2, 3, 4, 5, 6. That's it? You had a class with me? Your hand don't go up? 7. You've had a class, you. Right? So unfortunately, only 7 victims. So for those 7, is the answer A, B, or C? A. All right. I'll get 7 answers now, okay? B. A. B. You had me before? All right. Who else didn't? Back row. Oh, you did. B. B. You've had me before. Did you have me before? B. B? You're good. You're a fast learner. So just like this was a clue right here, you still have a unit conversion factor needed, and it's essential. And the unit conversion factor from memory, just like this was from memory, 1 Newton is defined as a kilogram meter per second squared. Guess what a pound force is defined as? A pound mass foot per second squared. I'm going to pause right here. Is a pound force defined like a Newton's defined as 1 kilogram meter per second squared? Is a pound force defined as 1 pound mass foot per second squared?
No.
32. That's exactly right. 32.2. 1 pound force is defined as 32.2 pound mass foot per second squared. How do you know that? How do you know what a Newton is defined as? Somebody defined it. There you go. All right, so what you do is you see that I can use 1 unit conversion factor as either 32.2 pound mass foot per second squared pound force, lbf, or it's equal to pound force second squared per 32.2 pound mass foot. Can I use either version A or version B? Are they the same? Professor, they're not the same. Look, one's got a 32 in the numerator and one's got a 32 in the denominator. How can they be the same? It's just like 12 inches is equal to 1 foot. True? So the unit conversion factor is 12 inches divided by a foot if you would like to go from feet to inches, or 1 foot is 12 inches. You're double talking. This is just getting me more confused. I mean, you're repeating the same thing over again, so it becomes all twisted. It's like the cashier you're trying to trick up. You're trying to, pay $10 for a $2 thing and then get this change and then insert this, and before you know it, the guy walks away with $20 of change plus his $2 purchase. No, I don't think so. All right. Does this make sense? A or B works? And the one we want to use is B. That's right. So what you multiply right in here, which I didn't leave enough room for, is this right there. And now we get the weight as 1 pound force, which is congratulations to everybody that participated. And so the weight is 1 pound force. That's the weight of 1 pound mass at the Earth's gravitational field. So, next question. G sub C. I've seen G sub C. I know, you shouldn't have seen G sub C. We'd like to bury some things in the closet, right? Put it in the cemetery and leave it alone. But every now and then you'll see this equation. They'll say, F equals to ma. I've seen that equation. Newton's second law, right? Then they'll say F equal to ma over G sub C. What? Have you ever seen anything like that? Very confusing. I'm glad you haven't. But now I'm exposing you to something when it should be left off, But anyway, this is the same equation. Guess what G sub C is? 1, which is 32.2 LB M LBF. True. You're ahead of me. Your brain is working. True? So anyway, you want to, sometimes people will see that G sub C and they'll say, well, that's equal to G. No, one is one dimensionless. We use it as a unit conversion factor to help convert units. And one is actually full of dimensions, not dimensionless. And if I drop an object at Earth's gravitational field, that's exactly the acceleration it'll experience. True? So if I take an object right here and I let it go, does F equal ma apply? Right? If the only force on it is the weight, won't it be accelerated by the weight pulling it down? What's the weight? M times G. I cancel. That's why they say G is the Earth's gravitational acceleration. True? And so if I wanted to report a free fall, it'd be 9.81 meters per second squared. That's the acceleration. True? Okay. Let me ask you this. I come back over here. I have a little scale. And the weight is the force needed when I put the chunk of mass on there to not let it fall. And so now weight is equal to M times G. I remember in SI, G is equal to 9.81 meters per second squared. Can I write that G is equal to the weight divided by M? And we just said 9.81 newtons is precisely the weight of 1 kilogram. Can I express G as 9.81 newtons divided by 1 kilogram? You know, that's really a more convenient G, isn't it? When you talk about supporting something so you get its weight versus letting it go and watching it accelerate. G is 9.81 meters per second squared if I'm letting it go. G is better described as 9.81 newtons per kilogram if I'm supporting it and just holding it steady. True? Here's another one. If I let it go, and I like to talk about feet per second squared, I let it go and the acceleration is 9.81 feet per second squared, just like meters per second squared is acceleration. True? That's the same rate of acceleration, right? I come over here. If I put the weight on my scale, it measures 1 pound force. 1 pound force. How many pound mass did I have to put on that scale to get a weight of 1 pound force? 32.2 pound mass. Your brain is fast, but sometimes you drive fast and you go off the curve. Remember, I had a scale. I put some mass on it, and I looked at the scale and said, hey, your weight is 1 pound force. How much mass did I put on that scale? 1 pound mass. Did you know that G can be expressed in 4 different ways? 2 in the SI, 2 in the USCS. This one's really convenient, SI for acceleration. This is real convenient in the SI for weight. This is real convenient acceleration. This is real convenient in weight. This one looks really, really easy. Almost too easy. You mean G is 1 pound force per 1 pound mass? It doesn't make sense. Does it? How many people are now thoroughly confused? I'm sorry about that. Well, you're honest. You're raising your hand. Here, let me do this. Let's start with G is equal to 32.2 foot per second squared. Can I multiply that by 1 and will that still be G? Can I multiply it by 32.2? Let me do this. Can I multiply it by 1 over G sub C? G sub C was just 1. Can I replace that to be 32.2 pound mass foot per second squared pound force? Isn't that 1? Wasn't that 1? Agree? So looks like it's 1 pound force per 1 pound mass. Do you agree? All right. Let's continue on. Pressure. Force per unit area. So if you do a free body diagram on the piston, you have a force pushing down on the piston. You have the atmospheric pressure maybe on the outside of the piston. You have the weight of the piston. Then you have the cross-sectional area of the piston. You can calculate the pressure of the gas underneath the face, the bottom face of that piston pushing back up. True? Know how to do a force balance like that? Sure, it's from statics. Let's talk about measuring pressure using a barometer, manometer, Borden tube. Each of those measure different things. If you've had a class with me, I like to talk like this, so bear with me, okay. So I take a barometer. It starts with a cylinder, a long, tall glass, visible, I can see through it, cylinder. And it's open on one end and closed on the other, right? Okay. Then I hold it up in the air, right? What's inside the cylinder? Air. I have a vat filled with liquid mercury, Hg. Liquid mercury. Conceptually, I'm doing this. I take that cylinder and I don't change it, anything. I just push it down into the vat of mercury. What happens to the fluid that's inside that cylinder? Is there still some air in there? Has some mercury gone inside? Is the mercury to this level and the air compressed to all in here? No. Probably what's going to happen is I get mercury compressed a little bit, but the mercury really doesn't go in there much. Just a little bit in, and then the pressure of the air gets squished a little bit, right? All right, but it's mainly air. I completely submerge it, right? Is there still air? And it's probably the air is, the interface is probably like this. The volume of the air is reduced a little bit because it's higher pressure. But then I take and I turn this, and I turn it like this. And what happens to the air? It bubbles out. What fills the tube? Is there any air in the tube? It's all filled, completely filled with mercury. True? I now take that tube and I rotate it back like this. Is it filled with mercury? I then bring it up and I just bring a little bit out of the mercury surface, right like that. Tell me, what's inside the tube? Is this all mercury, 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 mercury all the way up to the top of the tube? Or does the tube stop and now there's something else in the tube on top of the mercury? What is it? Vacuum. How about I raise that tube a little more? How about I raise that tube a little more? I know I had to get a long tube. Sorry about that. I'm stretching the tube as I go. First of all, you got to do this one right. Is the whole thing, remember here, right here I kept it all. Below I bring it out. It's all filled with mercury, true? I now bring it out, a little bit out, just an inch or two out of that mercury vat, pool of mercury. What's inside the glass tube above the surface of the mercury? 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 All right. So it's all mercury. Why isn't there nothing up there? Let me ask this. If I take a pin and I drill a little hole in the top of that tube right there, what happens when I get the hole punctured through and I remove the pin? What's going to happen? Air is going to go in, or the mercury going to squirt out? Air's going to, no, it's right at this height. It's right. It depends on the higher pressure. So given the illustration, for this case right here, get rid of all this, right? Given that illustration, with the pressure just inside versus the outside, the air pressure versus the mercury pressure on the inside at this position right there. Which one's higher? They're the same. Well, then air is not going to rush in when I make a hole. The mercury's higher. Then when I make a hole, the mercury is going to gush out like an oil well. Right? Or if the mercury pressure is lower, when I make that hole, the air is going to gush in. Which way is it going to go? I'm going to make sure we have good participation here because I don't know if everybody's playing like don't want to talk. So you're kind of quiet over here. Do you know what's going to happen?
I mean, I guess like if you just keep it at the same height, I don't think anything would happen.
That's why I ask these questions. All right. Let's see. I'll pick on somebody else.
I think the mercury is going to go back in.
So the air is going to come in and the mercury level is going to fall. All right. What do you think? Same thing? All right. Same thing? All right. So I know what's going on in your class. If you can let me know, like, I'm really lost, maybe, or, you know, body language, I can read it pretty good, but let me know. So if you think they're right, the air is going to rush in? Yes or no? Yeah. So if I continue to raise this, the mercury will continue to be pulled up, okay, until I get this so tall that something special happens. The glass, I pull it up, and the mercury stops coming. And I have a glass tube, and it's long enough so I can even pull it up some, better stay with the color of the glass tube, pull it up even higher. And when I pull it up even higher, the mercury level stays the same. That makes sense? Now the question is this is all liquid mercury, just like this is all liquid mercury. What is in here? Vacuum. It's really mercury vapor, but it's such a low pressure. The vapor pressure of mercury at room temperature is so low that there's very few mercury vapor molecules or gas molecules that is essentially a vacuum. There's a little pressure up there, but it's the vapor pressure of liquid mercury at that temperature. Small. True? If I take a needle and I poke a hole in it, what's going to happen? Air is going to rush in because it's going from atmospheric pressure to a vacuum. It's really going to rush in, and it's going to fill the vacuum and all that mercury is going to fall down to the lower level. True? So what we can do is we can do a free body diagram of the mercury column. The pressure acting on the top is 0 pressure. The weight pulling down is the mass times G. Man, I forgot what G was. It's my gravitational acceleration or my Earth's ratio between weight and mass, if you want to give it another name. But nobody will understand you. You just better call it Earth's gravitational acceleration. True? And then on the bottom, we cut this free body diagram to be right there because I know the pressure right there because hydrostatics, that pressure and that pressure are the same. We have to really prove that. That's Stevin's law, but that's true. So that pressure is right here, PATM, times the area gives me the force upward. True? The force upward. The weight is down, mg. M is rho times the volume, A times the height, h, going up of the fluid column, h. Is that the mass? Rho area h times g gives me the weight. True? So we say that good free body diagram, weight down, force up due to the hydrostatic pressure. You get PATM times area is equal to rho times the area times h times g. Do the areas cancel? And what we find is the atmospheric pressure is measured as rho g times h. A lot of times you say, oh, I can measure the inches of that fluid standing in my barometer. This is a barometer. So here is the long, slender glass tube. There is the vat of mercury. It's right up in here, vacuum. It has to be longer than about 30 inches tall. 30 inches, you have your hands 30 inches. Or 760 millimeters tall. How many people can give me a good meter length between their hands, right? Right? Now give me 760 millimeters, about 3/4. That needs to be that tall. We're not talking a slender little, we're talking it needs to be about a meter long so you have enough room up there, right? And that will measure, that's your height. So if you take that height, measure, multiply by rho of the fluid in this column times G, that will give you the atmospheric pressure. That pressure that's pushing down on the surface right there. That's how a barometer works. Thumbs up if you agree. What class is this? How many people deja vu from thermo? Covered in thermo. So well, you're kind of embarrassed to even have me speaking like this. Mastered that concept already. Or no, probably okay. Let me have a review. I appreciate a review. Right? Good. So let's continue on now. So a lot of times they'll talk about the atmospheric pressure. They won't report it in, let's say, kilopascals. They'll report it in inches of mercury column, or centimeters of mercury column, or millimeters of mercury column. Now let's say mercury, it's pretty heavy, it's pretty dense compared to water. Let's say the mercury is too expensive. I want to do this out in my lab. I want to do it with water. I want a water barometer, water-filled barometer instead of mercury, right? How tall a one do I need? Well, what's the difference in the density between mercury and water? Mercury is about 13.6 times denser than water, right? And so for the same pressure, instead of the density of mercury, I need the height of the water is going to be the density of water times G. This height of the mercury, we already said, was 760 millimeters, or about 30 inches. 30 inches. 30 inches. The G's cancel. The density of mercury is 13.6. Density of mercury is 13.6 times the density of water, liquid water. It's much denser, okay? So we could put the 13.6 times rho of the water there, cancel the rho of the water. And so the height of that water for the same atmospheric pressure has to be 13.6 times 30 inches. That height of the water column is about 407 inches. Anybody, can you do that? 407 inches? Convert it to feet. It's around 34 feet. Ooh, I'm not going to be able to stretch 34 feet. For a minute, I thought I could get 407 inches, but then I had to adjust my attitude. I'm 6 foot, put me on top. That's 12 foot, put me on top. That's 18 foot, put me on top. That's 24 foot, put me on top. That's 30 foot, put 3/4 of me on top of that. Sometime when you're goofing off, you look at a building and say, I think that's about 34 feet over there. You have to get a tall building, side of the wall. That's how tall that water-filled barometer needs to be to measure atmospheric pressure. Good? Thumbs up? Let's go on. A manometer is used to measure a difference in pressure. So if I want to know the pressure here compared to the pressure here, so we have a difference in pressure, right? So let's say this is state 3, that's state 2, that's location 1, 2, and 3. Those are 3 locations. Let me do this. Let me ask you, how is the pressure at 3 compared to the pressure at 1? How is the pressure at 3 compared to the pressure at 2? How is the pressure at 1 compared to the pressure at 2? I just want to know which one is relatively. So what we'll do is we'll take the first 2 rows, and the first 2 rows get to answer the top first question. Or First two rows only. This question right here. P3 greater than P1, less than P1, equal to P1. I tell you what, you're the first two rows. You answer this question. How about the pressure at 1 and the pressure at 2? Okay. Is the pressure at 1 greater than 2? First two rows only. Equal to 2? Or good. So it's equal to 2. Perfect. Now, the next two rows back, rows 3 and 4, right? You answered this question. What about P3 and P2? P3 versus P2, which is the higher pressure? Pressure at 2 is greater? That's right. So P3 is less than P2, true? All right. The very last two rows. What about P3 versus P1? P3 versus P1. Is that true? You all agree? P3 is lower? P1 is greater? So P1 minus P3 is a delta P that I want to calculate, and it's a positive quantity. True? Is that true or not? All right. So what is it equal to? Is it equal to P1 minus P2? Is P2 minus P3? That it? Is that equal to rho of this fluid in the manometer, whatever the rho is in the manometer, times G times H? It is. There you go. So really a manometer is used to measure pressure difference, and it's a density, gravity, and difference in height in the manometer. How about a Borden tube? Well, it's a device, and I know I have one. I want to pass it around. This is a gauge, right? And you can unscrew the lid, and then you can push out the innards and look at it. And right there's a Borden tube, just like in the illustration. And as the air, or this is for refrigerants, goes in here and builds up pressure, it takes and flexes out this curved surface. It fills this tube, and it makes it want to go straight, and it flexes it out. And as it flexes it out, you can see it rotate the dial. You could feel it, the Borden tube. So that's what it does. It straightens it out. There's a linkage over here to indicate the movement of that dial. Let me do this. I'm going to pause for a minute. All right, so the gauge pressure, I'm passing around one of these air tire pressure gauges, and you can take a look at it. What you can do to get it to work is pull the top off, and then gently from the bottom push up, and then you'll get the plunger out. And once you get the plunger out, you can actually tip it out, but you got to please put it all back in the same order, right? So that the next person can see it, how it works. Guess what's inside there? S-P-R-I-N-G, a spring. That's what's inside there. And a little rubber plunger. So the air, actually some air comes out of your tire and fills a tube, compressing that spring. As it compresses the spring with this plunger like this, it pushes out so you can read the indicator. There's a little plastic for a little friction right there, such that when you take it off the tire to visually read it, like you bring it up to your face to read it, right? Then this air will come out, the spring will push the plunger back to its normal place, but there will be a gap between the end of the rod that was pushed out and there. And then you know what you do when you want to take another measurement, you push the rod back in, a little bit of friction with this plastic holder right there, just a little bit of friction, right? So that it doesn't, when you hold it up, it doesn't slide out. Or when you can probably flick it out if you wanted to, but don't do that here. You may flick it into your neighbor's head. You know what I mean? It's just a little friction there. So that when you fill it up, take another pressure, the plunger seals, pushes down, more air pressure in the tire, the further that spring is compressed. Hooke's law, proportional, constant of proportionality, right? Good. So now we hook up with this gauge to measure the air pressure in the tire. So it's measured from atmospheric pressure. That's the gauge pressure. Because it's not measuring anything out here, I've got to put it on higher pressure. So it's measured relative to atmosphere. Atmosphere is around 15 psi. So if I measure 30 psi in a tire, what's the psi absolute? The absolute pressure of the tire with respect to vacuum. It's 30 plus 15, around 45 psia. True? So 30 psi gauge plus 15 psi for the atmospheric pressure gives you the 45. Vacuum pressure is difficult because some people talk about vacuum measured down from atmosphere. Sometimes people talk vacuum measured up from absolute vacuum, 0. It's not easy. You have to pay attention. And there's a lot of units for vacuum pressure. There's inches of mercury relative to the atmosphere measured down, absolute measured up. There's torr, or a torr is 1 millimeter of mercury. So 760 millimeters of mercury is the atmospheric pressure measured up. Or 1 torr, or 760 torr. Okay. They're the same. A torr is 1 millimeter of mercury. PSI. PSI from 0 up to 14.7. A vacuum percentage going down. And then micron, that's even a special unit. A micron, 1 micron is 10 to the minus 3 torr, a millitorr, a micron, 10 to the minus 3 torr. Okay, they use microns in HVAC applications. What's heating, ventilation, air conditioning? Where you ever have a service done to your refrigeration system, your air conditioning system, maybe you got to replace a compressor, an A coil, expansion valve, service it. They pull a vacuum. They measure that vacuum in torr. Usually they want to get it down to 500, no, not torr, microns, 500 microns even. If you're really good, you get it a little lower. But you want to get it into that vicinity. So you'll hear people talk about the vacuum pressure in microns. It's not easy. The bottom line is there are so many units for pressure, it's so confusing. This is the most confusing one. Length, it's pretty easy. Miles, feet, inches, kilometers, clicks, that's no problem. But the pressure, kilopascals, pascals, megapascals, bar, millibar, ATM, inches of mercury, where they tell you the temperature of the mercury so you know exactly the density of the mercury. The inches of water column, and you know the temperature of the water column so you know exactly the density of the water in the column. Torr, we just talked about that. PSI-A, PSI-G, what? Kilogram force per centimeter squared? Isn't that the answer I asked you about? What's that gauge reading on that one side with a kg? Per centimeter squared. Pretty neat, huh? So what's a kilogram force? Man, it's just like a pound mass and a pound force. If you put a kilogram mass on a scale at Earth's surface and it reads kilogram force for its weight, guess what 1 kilogram is going to show for its weight? 1 kilogram, not 9.81 kilograms. It'll be 1 kilogram force. That's why you guys can say, hey, I don't know my weight in newtons, but I know my weight in kilos. True? Centimeters, and that list continues. I didn't even put microns on it. Here's this gauge. I remember the first time I took physics, and I was doing something for the summer. I had to have these dash on my car. It was the 69 Mustang, no, what was it, 69 something. And I had a special, tubes running there to get the real oil pressure and the real, I can't even remember, I had 3 gauges. I was probably, I don't know, voltage or something. Anyway, you had to get a pressure, and these pressure gauges had kilograms in there, just like that pressure gauge. I was so confused. I had learned it in my physics class, and here I was looking at a gauge, and it had something like this for a unit. What? Kilogram, not even a kgf per centimeter squared. I was so confused. But I think this is a common sort of non-standard metric system of pressure out there. Maybe it's old school and going away, but there you go. Notice, don't use pressure gauges in the low vicinity, right? But if you're up in this vicinity, what is 2 of those compared to 30 psi? You can take that gauge as you're passing around. The one side says kg, flip it over and see if it says around 30 psi. All right? So there you go. So what is 1 kilogram force per centimeter squared, roughly? What is it? It's around 15 psi. It's around 1 atm. It's around 1 bar. I didn't say precisely, I said around. Right? Right. Because you can see that 10 is around 150. So, all right, we move on. Let's go to something easy like temperature. True? We really want to master pressure. We really want to master temperature. So you put on your Celsius. It's a relative scale. In SI, the Fahrenheit relative scale in the U.S. customary system units. Fahrenheit's only used primarily in the U.S., Solomon Islands, or some other, not very many places. And we know the boiling point of water. At 100 C, 212 F. True? Then we have the freezing point. 0 degrees C at 32. True? And then let's take a look at this. You have the absolute temperature scale. So you subtract 273 from degrees C, you have Kelvin. You can come down and there is absolute 0 Kelvin. This is a measure of hot. This is a measure of cold. You can only get so cold. You can continue to get really, really hot. But so cold, you can only go so cold. Can you get a temperature of -5 Kelvin? Physically possible to get a temperature of -5 Kelvin? Yes or no? No, it's not. It's below 0, absolute 0. It's impossible. Professor, you just telling me this, but some people somewhere in Siberia get it that cold? No. It's impossible. True? Now, -280 degrees C. Possible? -280 degrees C. Impossible. And yet, I've told this to a lot of classes. I've sat through a senior design presentation, and students are up there, and we have the temperature as a function of time, and here's 0, and here's 1,000, and here's -1,000, and it's hot, and then it gets cold. What temperature scale are you working with? Could that be Kelvin, that you have a -1,000? Oh, no. Must be degrees C. Could it be degrees C? Well, the computer gave it to me. So that's a true story, unfortunately. 0 Rankine is the same as 0 Kelvin. And then the difference between them is you subtract off the 460. So you subtract off 460 from or you add to 460 to get to Rankine from Fahrenheit. The difference between them is 460. All right. Notice the red line right here. What does that indicate? The same measure of coldness. -40 is pretty cold. But it's the same degree of coldness at -40 in degrees C and degrees F. It's a very unique place, right? So normally if somebody says, oh, it's 100 degrees F or it's 100 degrees C, which one is hotter? Degrees C is a lot hotter, right? Okay, they say it's -100 degrees C and -100 degrees F. Which one is colder, or you want to stay hotter? Okay, which one's warmer? I know both are cold. Which one's higher? I thought I knew all this stuff about temperatures. It's challenging, true? Which one's hotter? C? Yes. Huh? F? What are you guys going to do? You can get your calculator out, plug in -100 and convert from C to F. Boom. You'll get the answer that way. So, all right. How about this? Negative, let's say 250 degrees C, negative 250 degrees F. Which one's hotter? That's more clear, isn't it? More clear. But both of these are below the 40 where there's a crossover. So which one now do you think is warmer? Degrees F or degrees C? Negative 100 degrees F or negative 100 degrees C? Which one's warmer? F. Okay. Well, I'm going to encourage you to struggle with some of these concepts, right? Density, everybody knows that. And specific volume is reciprocal of density. True? How do you like that? We covered that pretty fast. Specific gravity. SG for specific gravity and then specific weight gamma. All right. Specific gravity is a ratio of the substance mass density of the substance of interest compared with a benchmark. And because we're in fluid mechanics, what do you think our benchmark fluid is going to be? Water at 4 degrees C. 4 degrees C liquid water is 1,000 kilograms per cubic meter. So this will be water at 4 degrees C. And what was the specific gravity of liquid mercury? 13.6. That's true. Right. Right. What is, let's say, the specific gravity of ice? Solid frozen ice. Is it greater than 1 or less than 1? Very good, less than 1. Now, the specific weight, that's going to be rho times G. Rho times G. And this is really where that discussion of G comes in handy. So if I have 1,000 kilograms per meter cubed for water in SI units, isn't that water mass density? And I have 9.81 meters per second squared. What is the gamma? I can't write gamma. Come on now, get gamma. Here you go. What is the specific weight of water, liquid water, in the SI units? True? Now, if you're over in the U.S. customary system of units, the mass density of water is 62.4 pounds per cubic foot. Professor, pound. Is that pound force or pound mass? I'd like to be clear. I'm talking mass density. It's pound what? Mass. And our G, because I'm calculating gamma, the specific weight for liquid water in U.S. customary system units, 32.2 foot per second squared. True? So what is gamma when I do that multiplication? 62.4 pound force per foot cube. And it's a lot better, instead of using that version of G, why don't you use this version of G, that the weight, 1 pound force, of 1 pound mass at the Earth's surface is that. It's 1 pound force over 1 pound weight. That's the better G for this problem, right? True? So there you go. So this makes it really easy. So there was a civil engineering faculty, and the students in civil engineering, you take them into the lab, and he had the technicians build 1 cubic foot. Everybody, you know, if you want to get a good measurement of a foot, that's about it, right? Does that have a hole in the bottom? Sorry. But that's a cubic foot, right? And then he had a handle to it, and he would fill it up with water, and he'd say, okay, civil engineering students, come over here and pick this up. And they'd come over there, and 62.4 pounds. You really get a sense of how heavy that is. That's just 1 cubic foot of water. That's really not much water. I think some of you use more than that just to shower. 1 cubic foot plus some, right? Kaboosh, all over. But that's a lot of weight in 1 cubic foot. If you had 1 cubic foot of mercury, I don't even know if somebody could pick it up, huh? Probably not. Surface tension. The book uses different symbols. Sigma, or this textbook or whatever I grabbed it from, use this symbol for surface tension. But it's different substances have different surface tensions. Notice the new units for surface tension, newtons per meter. A lot of times that doesn't make sense, but if I say it's a Newton per meter and I multiply by meter and a meter, I get a force per unit area. Newton times meter is that's not a force. It's a joule, sorry. An energy per unit area, true? Newton meter, joule? Okay. So that was Newton is the force per unit length, and then you get the joule per unit area. Sometimes it's convenient to think of it as energy concept, not necessarily a force concept. But here's liquid water, 20 degrees C, 100 degrees C. What happens to the surface tension as you heat up liquid water? Go up or down? Down. That's why you like to wash clothes with hot water if you can. It helps break in, get that water inside, knock out all the dirt particles out of your clothes and bring them out. Wash with hot water. Also, you put laundry detergent in. What does the laundry detergent do? It's a surfactant. It knocks down the surface tension, helps the water penetrate deep into your fibers of your shirts and pants and stuff and bring out, by agitation and flow, the dirt. Oh, here's soapy water at 20 degrees C. Even if you have to wash your hands with cold water, use a little soap. It really helps bring that stuff off your skin. You ever done that? Wash with just water and then get some good soap and then wash and then look at kind of the darkness, the dirtiness of the soap suds. True. Alcohol, glycerin, mercury. Mercury likes a high surface tension. It really likes to hold itself together. If you ever took mercury droplet, don't do it. Put it on a piece of glass, it would lay there like a bead holding itself together. Where does it come from? Well, the molecules, there's a traction, a force between the molecules, so they call that bond. When you have a surface up here, there's no molecules up here to bond to or up like that. Hence, they have just a stronger bond because it's missing. These are missing up here along this surface versus if it's submerged. So right in that surface, it's like a net force pulling it in. And so a round surface, it'll pull it all together and hold it like a bead. A water droplet falling in the air forms into a certain surface, and the surface is like a bead if it was in a vacuum, but the aerodynamics make it change shape. And stronger bonding between different materials. You can solve some problems. Let's say you had a soap bubble. Anybody ever play where they blow it? And what you have is the inside of the bubble, it's air, then a layer of a soapy film, and then the outside. And the pressure on the inside is different than the pressure on the outside. Do a free body diagram by cutting that soap bubble in half. You have a force, the surface tension around this edge and that edge. That's why there's two in this equation right here. And so you'll have the force pulling on that edge, and then you have the pressure difference pushing on a cross-sectional area. That cross-sectional area is pi r squared, true, pi r squared, times the pressure difference equal to 2 times the surface tension, that sigma times length gives me a force. A surface tension sigma times the length gives me the force. Well, what is the length? It's 2 pi r, true? So the R's go, pi's go. I get 4 sigma equal to R delta P. Hence, delta P is equal to, I just messed up something, 2 pi R squared, delta P, 2 sigma. Don't I have a 2 and a 2? 4 sigma over R. Okay, it's either 2 sigma over R or 4 sigma over R. Pardon? For a soap bubble is 4. That's right. This is for a soap bubble. I wrote it down for a solid. 2 sigma over R. Okay? So that's the pressure difference. Vapor pressure. If I take a piston free floating in the cylinder, but it seals it, and I put a little liquid in the bottom, and I bring it into thermal communication with something that's at temperature T1, but the temperature T1 isn't so high, it just all stays all liquid at that pressure that the liquid's at. But if I then replace it by something a little warmer, how do you like the color coding? You find that some of that liquid can begin to change into vapor. And for this temperature, there will be some pressure, vapor pressure. Okay, maybe I have to add some more weight up here to get it to balance out and stop changing. But there'll be a particular vapor pressure, and it's a function of the temperature at which you can have a two-phase equilibrium mixture. True? We look at water, we like to talk about water. If it's at a temperature of 100 degrees C, what is the vapor pressure or the saturation pressure? Around 100 kilopascal, around 1 atm, 1 atmosphere. That's why it boils at 100 degrees C. True? If you had it at a higher temperature, you would have to have more weight to keep it to be two-phase. If you had it at a higher temperature, you'd have to have more weight, so that saturation pressure may be up in the 500 kPa range. So typically these curves go like this. The shape is very strong. As you increase temperature, the vapor pressure, saturation pressure greatly increases until you get to a maximum, which I didn't show, where you get to the point out here. What was that point called? Very good. Critical point. Flow between two parallel plates. What we want to do is just talk about this type of setup. I have a boundary on the bottom. It's not moving. I have something up here that's making all the fluid at this top layer move to the right with the velocity u. All right? It's just going to be continuously shearing it. Remember, it'll continuously deform with a non-zero shear stress applied. So the velocity profile will look kind of bland. It'll be a triangular shaped velocity profile, meaning if I come halfway down into the fluid, it'll be half of the top speed plus half of the bottom speed, which is 0. So it'll be half of it, of the top plate speed. If I come down 3/4 of the way, well, if I go 1/4 of the way down, you know, it's a linear velocity profile. All right. And what we do then is we can talk about the shear stress at the top. The shear stress at the top is the force that you're having to apply per the unit area that's up here at the top. So the tau is the force per unit area, shear stress. Okay, shearing. You can do a free body diagram and come down into the fluid such that it's still in the fluid but real close to the solid right here. And I have a shear stress tau on the top plate in the right direction, to the right. And on the bottom, I'm going to have a shear stress in the bottom going in the opposite direction, holding it back. If there wasn't something holding the bottom plate back, then it would actually be dragged along with the fluid. The fluid viscosity would want it to move to the right, and it would go to the right. True? Okay. So you have a force holding it back to the left, and that translates into a force per unit area as shear stress. Let's do this. Let's do a volume free body diagram that's half. Let's do the top half, or let's do the bottom half. Doesn't matter. Okay. If we do the top half free body diagram, I have the shear stress to the right. Got it? Magnitude tau. Some of the forces in the x have to be equal to 0. I'm going to find that there's a shear stress in the fluid, which means the fluid below that is going slower. Hence, it's retarding or pulling back and exerting a shear stress back. How about if I look at the red control volume? I said I already knew that the bottom surface is applying the shear stress that direction. Guess what? It has to be this one there. It has to be so the fluid above the red control volume, the bottom control volume, is making it want to flow in the positive x. Just like the fluid below the blue is wanting it has a shear stress in the negative x. Well, you could do this anywhere. What you find is that the shear stress, tau, is the same no matter where you cut it. Can you see that? Tau is this uniform through that for that velocity profile, which is triangular shaped. And now what is the equation that tells us this? Or let me ask you this. If I have a different fluid in here, let's say I put in water, maybe I put in oil, maybe I put in some fluid that's very viscous, like tar, right? Something very, very, oil is pretty viscous. Or I put in air, not so viscous, true? What you'll find, to have the same top speed up here, u, for the same magnitude, which one do you think I'm going to have to apply a greater F for the same area? For the oil, right? This will have the greatest F. Which will have the least, the water or the air? The air. And so this is a property of our fluid, and really it shows you what that shear stress is as a function of the shear rate, and air has a low, water higher, oil even higher. And there's our viscosity. Our viscosity, mu, it's a constant proportionality in law of viscosity. And the law of viscosity is something like tau is equal to mu du dy. So for that velocity profile like this is y going up from the plate typically. U is a function of y, but it's u is the x component of the speed, but it's linearly increasing with y. The rise over run, it's a constant. For this problem, this was a constant. And it gives you the viscosity mu over du dy. All right. I've got a couple minutes and a couple slides, but I'm going to stop there. And